Thank you very much. Yeah, so as Robert already mentioned, my name is Joris. Apologies to those expecting Chris here. I hope I don't disappoint too much, but yeah, I'll try to do my best to go through the slides. That Chris prepared the slides, so that's at least something, right? I'll give an advance warning, right? I'm not too into the low-level details here, but I should be able to guide you all through the presentation. So we'll ask any questions if you have them after the fact. All right, so my name is Joris, as mentioned. I am the technical team lead for Julia Sim when it comes to applications and turning it into a product. So Julia Sim is our simulation environment, model-based engineering based on top of Julia. It's a proprietary product developed by Julia Hub. So just quick intro into Julia. I guess most people have at least heard about it. Who's using Julia? Just a quick show of hands. That's not bad. So quickly, just like what is Julia for those that have never heard of it? Julia is a high-level language. It's been around for about 12 years now. It was announced at Valentine's Day 2012. So it's been around for a while. It went 1.0 in 2018, so it's been sort of at a stable versioning rate ever since. So Julia is a high-level programming language that was described as by the creators. They made a new programming language because they were greedy, so they wanted everything, right? They wanted speed, they wanted high expressivity. They just wanted to have a language that was nice to work with, but could just tear through data, just run really well. That was its original sell. I think Julia is indeed a fast language. That's something you'll hear people talk about a lot. But it's a lot more, right? It gives I think once you start using it for a long time, there are a lot of other benefits that sort of become apparent, some of which we'll see during this presentation as well. So you can see here, compared to some other languages, right? Julia sits basically at the bottom left, which means that it's a highly expressive language, but it's also very fast. So you get the best of both worlds. Who doesn't want that? And I think one particularly interesting thing is relative to more traditional high-level languages, right, where they're very nice to prototype in, right? This is why people use things like MATLAB, Python. They're very nice to prototype in. It's very nice to express your ideas that you have typically around scientific research or engineering. But then when you want to make things fast, you have to move into other languages like C or Fortran to get really speed benefits of being able to crunch through your data fast, or to solve, in this case, solve equations quickly. So one of the nice things, at least I think, about Julia is that you can actually get the best of both worlds, but you can get there incrementally, right? You can write slow Julia code. Actually, there's a lot of it will be a lot of people's first experience is when you just start out writing Julia and you start writing it as if you were writing Python or MATLAB. You go, wait, this is actually slow, which is okay, right? You can still express your ideas, and then over time you can actually add when you learn how to make faster, or you can dig into the details of what makes Julia a bit faster, and you can start adding type information, things like that, to incrementally get better working software or faster working software. So you have the Julia community. It's basically Julia in numbers, right? We're steadily growing. This goes back to about 2016. As I mentioned, it was announced in 2012. I started at 2014. 1.0 in 2018. So you can see everything's steadily growing. Basically, there's lots of more and more video content available on YouTube. Downloads keep rising. The community forums get more and more active, and this year we actually crossed the 10,000 packages. I hope I'm standing in front of the slide, so I'll move out of the way a bit. We crossed the 10,000 package number. So as I mentioned, right, often one of the nice benefits cited for Julia is that you get these high-level programming language benefits without having to go to low-level languages, right? If you look in the Python community and you look or in the Python ecosystem, you look at things like SciPy or NumPy. The high-level interfaces are nice and in Python, but as soon as you have to get into performance-critical code, you have to go into C or Fortran, and you're calling into libraries like that, which is fine, right? That's a design decision. One of the downsides of that is if you if you are working on something, right, and you want to first get started, as soon as you hit a point where you need more performance and you know Python, well, now you also need to know C, right? That's a significant, there's two different ecosystems that you now have to know about. So what if we use Julia and its numerical packages as a backend for Python and R instead? Right, so one of the advantages that would give you is that you would actually get a lower entry to you still need to learn another language if you wanted that. However, that is another high-level language, so you can still express your ideas in this higher-level language without having to, for performance reasons, go into C-level code or Fortran and changing to a different ecosystem. One of the particularly nice things I've seen quoted a couple of times when it comes to the Julia ecosystem is actually that there is a large, when it comes to something like the differential equations package or that ecosystem, there are a lot of contributors. And this comes from the fact that a lot of people come in from their own sort of distinct areas of expertise, and they need something that's numerically faster or more stable, and actually can contribute that. The barrier to contributing code to the core ecosystem of differential equations is very low because they know Julia, so they can very easily contribute like new algorithms, things like that back. And they don't even necessarily have to worry about performance because, well, I've been in the Julia community for a while, and I know people pretty easily get nerd sniped. So if you just go, this isn't fast enough, or why is my Python package faster? I guarantee you someone will go in and sort of optimize everything for you, which is nice. You don't have to learn C. You don't even have to learn how to write performant Julia. Just have someone else do it for you. Now, the Julia community has been growing for a while, so there's a large set of existing tools when it comes to numerical packages, and there's a quite large developer community. I think I've seen numbers for the particular packages I'll be talking about today, that we end up with about like 100 contributors. Not all of them active all the time, of course, but there's a fairly substantive amount of people that are working on things like differential equation solvers and just other packages in the larger SciML ecosystem. Well, SciML ecosystem, you ask, what is that? Well, let's dive into that a bit. So what we'll primarily be focused on during this talk is a subset of that, right, which is about high-performance differentiable equation solvers. So the SciML ecosystem we'll dig into a bit later what SciML is. We'll keep it a bit vague for now. But basically what we have is, and this is one of the strengths of Julia, is Julia packages are very composable. So it's very easy if someone else has written a package, right? If you know things like open-closed principle and stuff like that if you're into software engineering. It's very easy if someone has provided like base types or function, right? It has defined certain functions like solve, right? This is how you, or types that'll help you solve linear systems of linear equations. It's very easy to reuse those and expand on them as well with new algorithms and things like that. So there's the SciML ecosystem has this basis of a number of packages that tackle specific numerical issues like solving linear equations, nonlinear equations, solving differential equations, just regular optimization, but they all tie in neatly together. And this is where a lot of the strength of this ecosystem comes from, is that people go like, oh, I have this piece here, what if and I have this sort of optimization strategy here, can I combine them easily? Typically the answer is yes, and if not, it'll take you like 10 lines of code. Right? It's typically very easy, if an integration doesn't exist yet, to add it. So one of the key things that people always bring up when we're talking about differential equation solvers within Julia is that they're really, really fast. Typically, they sit at the bottom of these types of graphs. So one thing I want to point out here, if you disagree and go like, wait, why is my thing so slow? There's this, I guess the QR code up there leads to it, but you can see there's this SciML benchmarks repository. So all of these benchmarks are completely open. So if you disagree or you want to add a new solver, file a pull request, right? These benchmarks are continuously expanded upon, so basically to keep an eye, to make sure that they are as fair as possible, so you don't get into arguments on blog posts about but you did X wrong. It's like, well, if you did X wrong, you know a faster implementation. Go ahead. Everything is available. But what that means is we end up with different equation solvers that are like 50 times faster than SciPy or MATLAB, or up to 100 times faster than DESolve in R. So that would be nice, right? If these are like ordered 2 orders of magnitude speed improvements. What if we could use those easily? So that's what we're talking about when we use those within Python. Now, it's not just about speed. As I mentioned, right, there's this broad community of people that are contributing to this. So that means that you get a lot of like state-of-the-art algorithms in these packages as well. It's very easy to try out different types of solvers on the same system. If you want to try something new, it's very easy to implement something new without actually having to change like the overall problem description that you're the problem that you're trying to solve, right? Because they all rely, all of these implementations rely on these interface packages that just, what do you need to know how to solve a system of differential equations? Well, just call the solve function on it, right? And then you just go. There's a bunch of different types of solvers. There are just some that are more stable in certain cases for certain types of problems. There are solvers that can deal with stochasticity in the differential equations. I'm not even going to talk about adjoints because I have no idea what they are. And one of the key benefits I think that we'll see a bit later as well is they can actually be parallelized pretty well, or extremely well actually, which brings along a whole different set of benefits. So for instance, it's trivial to run these solvers on GPUs. It's actually one of the key benefits of Julia. It's very easy if you have something that works on a CPU. It typically requires like literally a couple of lines just being changed to a different type, right? So instead of an array, you use a CUDA array, and now things run on your GPU. And this means you can get massive speed improvements. And the beautiful thing here as well is that this doesn't just work for CUDA. This works for AMD. This works for one API, and then as Chris always likes to say, he got an M1 Mac especially so he could put this additional bar on the side of this graph, even though it's not that impressive. But what is impressive that it just works. It's not if you have a different GPU, we're not writing specific implementations of a solver for a specific GPU. No, we can take implementations of certain data types that are optimized for a specific GPU architecture and combine that with the solvers that are defined in the SciML ecosystem. And then, so it's very easy to switch around and compare across different platforms as well. One of the recent advancements, something that people have been talking about at least as long as I know about it, which has been, I always say WebAssembly has been the promise for about a decade now. We're finally seeing things happen that way a bit, but we're actually able right now, as of a couple of months ago, on like the most recent versions of Chrome, and by recent I mean the ones that aren't released yet, because you need garbage collection. I believe that's the thing that's necessary, which wasn't available in WebAssembly until a couple of months ago. We can even take, at the very least, subsets of the differential equations ecosystem and compile them into WebAssembly so they just run natively in your browser. So that makes it very easy to basically go from your research phase, right? And that's, I think, a very important part here as well, is you're in your high-level language, you have a very expressive language to do your research in, but then when you want to bring it to production, you're not handing it over again and again and again. Right, before I joined Julia Hub, I was working for a different company. I think we had like 4 stages there, where someone was doing something in MATLAB that would get rewritten in fixed point, that would get rewritten in C, and then some parts would probably even get rewritten in assembly. That's a huge train to follow through, right? There's a huge supply chain to go through, and there's a large opportunity for errors to creep in. That's less of an issue when you're going with Julia, because you can stay within Julia and you can take it all the way down to machine code. So yeah, that's about it on what I wanted to say about the differential equations ecosystem in the Julia language itself. So can we get all this nice stuff in R and Python if that's what you want? And obviously the answer here is yes, otherwise I wouldn't be giving this talk. So here we actually have 3 it's the same example in 3 languages. Chris, I'm not sure how old the packages are. I believe they actually have been around for a bit. But so the SciML ecosystem has the diffeqpy and the diffeqr packages, which are wrappers around the differential equations ecosystem in Julia. So on the left here, we have an example of the Lorentz equations in Julia, right? So you define a function with the derivatives, keeping track of the derivatives and the input. It doesn't use the parameters or time here. You can set that up. You convert it into a problem, and then you solve the problem, right? This is what basically any of these things looks like. Typically, the majority of the work sits in the definition of your model. Now, with the diffeqpy and diffeqr packages, we can actually, well, you can see it's almost one-to-one, right? Obviously, there's some syntactic sugar here and there, and there's some slight language changes. But what happens here is that under the hood, right, this gets translated into, this just maps directly onto the Julia types. So you get already some nice benefits. It's even easy to move back and forth between, right? Well, you have to still rewrite it a bit, but you can probably get things pretty close. It gets even better though, right? Because one of the things that you typically have to do is if you're using a different language, like C or Fortran, now you have an entire different tool chain to spin up, which typically can come with its own its own challenges. Now you have to maintain 2 things. Are the versions compatible? It's no fun, right? I've been there. These particular packages, they actually provide full automation here. So they have not sure why they're called differently. I didn't write it. They have a setup and an install method that will just automatically install Julia, make sure the right things are installed, correct packages, nicely isolated so they don't mess up your system. And this also automatically sets up these necessary conversions, right, that you need to move between Python and Julia. Julia in general is quite good at this. There are many packages that provide integrations between these different languages. You have them for Python, R, Java. But these are typically just bindings of turning, or C even, right, to turn one data type specific to one language into another one. So if you're building software for other people, they don't even have to know that under the hood it's Julia, right? They don't have to set up anything additional. You just call that one function in your code, and you're good to go. Now, I have to be honest, I don't completely understand what Chris wanted to do with this talk, or with this particular slide. Well, I think I do, so forgive me if I'm wrong. So as people may know, Julia is a JIT-compiled language, just-in-time compiled. And because this code in Python and R that you see actually gets translated into Julia, right, it gets turned into Julia under the hood, you get these same JIT benefits because Julia takes care of the just-in-time compilation. And then we have our own, so there's a modeling toolkit, which is our modeling language in Julia. We can do all sort of cool symbolic stuff to simplify models and stuff like that, to get rid of extraneous equations, making sure things are stable, even before calculating anything. So just sort of a quick analysis of where we have these different performance overheads in this package, or right when calculating differential equations. So and it's been a while since I took a class on differential equations, so I lost a lot of knowledge there. But it's relatively easy. This is from a paper by Elizabeth Rush, and I don't know the other people. If you're trying to solve this set of differential equations, right, this amounts to, and this is where the sort of the speed up comes from, right? It's just putting it out into numbers. We're capable of taking these operations and just fuse them into a single function call inside Julia. Basically, this modeling toolkit and everything around it is a sort of an additional compiler on top of the Julia compiler. So we can perform all sorts of analyses while we're building the code for you that actually gets executed. So in Python, this just ends up being 8 function calls. In Numba, the fusion happens as well. And then you can take a look at how expensive it is to call a function, to call the final function, and that gives you like about a 30 times speed up in Julia, but the Julia code just executes faster, theoretically, of course. But this means you can, as you can see at the bottom, right, you can get some pretty extreme performance benefits over solving differential equation systems in Julia versus directly in Python or even using Numba. So again, similar to what I said earlier, right? The SciML benchmarks ecosystem. If you can, it's on the QR code. There are notebooks, Colab notebooks, Google Colab notebooks available that actually just run this in, where you can run this interactively and inspect for yourself that it's actually fast. So yeah, these are quite impressive numbers, right? Whether you have to wait for a week or half a day is, give me half the day. Well, give me an hour preferably, but it's just a lot, right? Faster feedback loops are always better, and I'll stick with that. But the real nice thing, right, as I talked about earlier, we have this GPU support, and as Chris calls it, right, that's the real parlor trick, is can we leverage this GPU acceleration that's inside Julia from Python and R? And the answer is, well, yes. And again, similarly to what we had just for the overall integration of diffeqpy and diffeqr, is there are setup methods that will just specifically install the drivers that you need, which you typically don't want to always ship, right? I'm not sure if anybody has ever checked how large CUDA drivers are, but they're big. They're like 1.5 gigabytes right nowadays. So you don't want to ship that to everybody, especially if they're not using it. So again, this also just automatically installs all the Julia packages, and you're just good to go. You have full automation of the GPU acceleration process from Julia for Python and R. And again, right, it's not just Julia, or it's not just CUDA. If you want, you can. If you have an AMD GPU, just import whatever package is specific, or whatever module is specific to your the GPU in your machine, and it'll just work. I don't know, right? I'm not familiar with the ecosystems, but according to Chris, these might be the first packages that are GPU agnostic in these ecosystems. I think I don't know what the difference is here. Oh yeah, this is the JIT performance. So for CUDA, right? So this, again, compared to PyTorch and Jax, same story, a lot faster. So you mentioned this sign, or I mentioned this sign. You might go, like, you mentioned this SciML. What's SciML? That's actually, well, I kind of enjoy it. I think it's quite a nice idea. So what about SciML? Stands for scientific machine learning. What does that actually mean, right? So you always have these sort of two camps nowadays in when it comes to solving problems. Is either those are two extremes, right? You're either in the data camp, you could just go, I can do anything with data, or you're in the hardcore, I can model anything or try to model anything camps. SciML says, well, why? There are downsides to both, right? If you need to learn everything from data, that's throwing away a lot of knowledge that you have, and you can't typically put everything in your equations because it just becomes intractable to solve. So this is actually what the SciML ecosystem is all about, right? It allows us to capture knowledge that we have, right? Things we know, just like from physics. Use that to build models, to solve those models, to even perform control on them, and then augment those models with machine learning based on real data that we obtain from real systems, to get to a space where we can get to better overall models. So as an example, right, say that we have a physical model that we know, like this describes a certain phenomenon, but the things that we measure, turns out they're not accurate at all. Now, what you could do, of course, is you could try to change the parameters of your known physics to get there. What you can also do, or what we do typically in SciML, is we add an error term, which basically we slap a neural net at the end, and then we put that inside a simulator. We solve for the ODE system, and now because you have the real world data, you can train sort of the missing error parts, right? The parts that you didn't know, but that are apparently there in your data, but that weren't described by your physical system. We can automatically learn what those pieces are, and then thereby basically fine-tune your model. And there's a lot of this is very basic, but there are a lot of cool edge cases that you can do with this as well. So one example here is this doesn't necessarily seem like something that's easy to learn, but say that, and I, again, not an expert, so forgive me. Right, this is a model, or this is data obtained from the two black holes, right, that rotate around each other. And so you can sort of, what we're doing here, or what we've done, what has been done here is sort of only describe like regular physics, and like you don't know anything about relativity theory, which I don't know that much, so that makes sense. But what we can actually do is we have gathered, right, or this group has gathered a large amount of data from the LIGO gravitational wave data. What it can actually do is you can start with your regular physical description and actually use the data that you've learned or that you have obtained for a relatively small piece, and reconstruct sort of the relativistic terms that need to be added on top of your regular physical description to learn. And you can see that these things are almost right. So the blue line is the known waveform. The dotted red is the learned. Well, we can learn this, well, relatively complex interaction of these two black holes from a relatively small amount of data, which is very nice, right? This means that there's a ton of examples. If you go to SciML, SciML.ai is the website. There are a ton of examples here that actually go into like chemical processes that are where you would, if you would just know, or if you just try to model the data, you didn't know anything about the underlying physics, you would try to extrapolate, you would be completely wrong. But using this combination, you can actually make correct predictions. So again, I don't know too much about this one particularly, but I'm sure other people do. You can also integrate Julia code and diffeqpy with PyTorch. That's all I have to say about it. I'm sorry. So there are obviously, right, there are some caveats to using something like this. There is obviously a performance overhead, right? You have to translate from one language into the other, right? You have to translate your data types, so there's some performance overhead. But even with that performance overhead, it's still faster than all the other implementations. So, yeah, it's overhead, but it doesn't matter if it's still faster. Not really. The automatic differentiation support does not have nice syntax right now. Those are things that can be ironed out. Yeah, and the JIT, right, because as I was sort of talking about, there's sort of a compiler on top of a compiler type situation. The JIT is restricted to just the mathematical operations that can be handled by modeling toolkit, by this modeling language and its corresponding compiler. But those are, I'm not sure if those are things that are getting changed. They might not be able to. Well, there's just some fundamental things, right? Things that aren't in Julia, you can't sort of. The influence stops somewhere. So if you really want to go all in, just use Julia. Right? Well, I have to say that I work for Julia Hub. But if you want to just get started and just compare to what's possible, anyone in the scientific community can basically step in and start exploring these ideas through the diffeqpy and diffeqr packages. So, yeah, about time. So that's it. Thank you.
Thank you so much. If there's questions from the room, please raise your hand. Yeah, go ahead.
So this has like a little bit of a wolf in sheep's clothing vibe, like Julia being kind of like a friendly language. Like we say that we're here because we don't like programming Fortran and C, but the other half is that you also don't need to write Python with Julia. And I'm just wondering, how is the adoption? Like, do Python and R people use the differential equation solvers? Are these popular? And is the Julianness of it kind of make people more or less interested in it?
So, yeah. So the question is, obviously, right? There's a sort of competitive nature to this, and then sort of the integration provides this wolf and sheep. We're trying to steal people away sort of idea from other communities. I get that that's a sentiment, right? That happens, and then sort of the follow-up question is, how do people from the R and Python communities adopt to Julia? I think as a lot of these cases go, right? It's a very visceral sort of reaction, right? These things almost become religious, right? It's where there are quite a few people that have indeed gone like, well, I just can't do these things in R, or it doesn't, or in Python, or it doesn't feel right. So sometimes people do get put off by, sort of as I mentioned, right? There is a different style of programming if you're going into like deep into Julia. Like if I could compare how I wrote Julia code, or how I wrote code a decade ago versus how I write Julia code now, because due to the facilities that the language gives you, basically your mind, you think about problems in a different way because it allows you to express the things that you have in a different way. So for some people, that really clicks, right? And sometimes you might need some guidance to actually get there. And so yeah, you can still get that sort of split where you go. I've met many people that went like, okay, so I tried, I had my Python or my MATLAB or R model, turned it into Julia, and I basically just, literally translated it, and it's slow, so I'm going to give up. Well, yeah, you have those. And on the other hand, yeah, you do have people that are full converts. One thing I think that is beneficial to things like this, where which I used to be one of, right? I was a full-on Julia convert, but within a group of people that was only writing MATLAB and was never going to change, right? But you still want to do, it's like, but I can't do these things in this other language, so I have to sort of do it this other way. So then having these types of things available where you can integrate with other languages is just very nice. Hope that answers your question.
Seems that Julia is solving not a second language problem, but nth language problem, and kind of substitute for you saying, okay, a lot of people likes prototyping in Python, we cannot do anything about it, and we will at least compile their code in Julia, not in Fortran. So it's kind of sentiment that I obtained from this talk.
Well, I think so. Yeah. So the idea, the question is, right? One of the things that Julia or the Julia community talks about a lot is this idea of a two-language problem, right? Or the sort of the high-level language versus low-level language, and having packages like these sort of feels like we're sort of giving up on that, right? If I'm paraphrasing you correctly. I see that, right? I get it. I'm not sure if that's necessarily entirely accurate. It's also about, as I sort of mentioned earlier, right? It is about being able to. Sometimes you might have a huge legacy, code base or model base or whatever, right? And you can't rewrite everything from scratch. So for cases like that, or for people that are interested in being able to compare things, I think that's the primary purpose of having packages like these, to facilitate this integration with other communities, to also be able to bring additional expertise into the larger ecosystem and community.
I think we have time for one quick question maybe still, and then we need to close. If there's anything else? If not, then thank you very much, Joris, for stepping in so late. I think we can all agree that you did a great job, and yeah, please give him another very big round of applause.
Thank you. Oh, I'm turned up, and I have stickers if anyone wants them. Obviously.